into the next lesson, we're going to be discussing the greatest common factor. A common factor is a whole number that is a factor of two or more whole numbers. So in this first example, we're going to list the factors of 16 and the factors of 28. Now I'm going to circle their common factors. So the common factors for 16 and 28 are 1, 2, and 4. Now we're going to determine what was the greatest common factor of those two numbers. Listed out the factors for 21. I've listed out the factors for 42. The greatest common factor of these two numbers is 21. At some point, as we're listing out the factors, if the numbers are not friendly, you might miss a factor. So let's do excuse me, I must have missed one. Now we're going to list the factors for 60 and 96 and find the greatest common factor. Again, they're getting increasingly more difficult. So I'm going to list the factors up there, then we're going to do the greatest common factor. So as I've listed the factors for those two numbers, then we found the greatest common factor of 12. But as we were listing them, sometimes there's room for error when you're going to have to list each of the factors. Now we're going to find a method to where you will not miss a single factor when you're determining what a factorization is for a certain number. You can also find the greatest common factor of two or more numbers using prime factorization. In our previous lesson, you did what was called factor trees. You did trees for each one of these. So let's put trees up on the board for each one of these. So as you do your trees, every tree could look different. Yours does not have to look like mine. But the totals, your prime factorization, will match. When you do the prime factorization for certain numbers, you go from least to greatest. So for example, the prime factorization of 16 is going to be 2 to the 4th power. The prime factorization of 28 is going to be 2 to the 2nd power times 7. List them from least to greatest. Now, in determining what the greatest common factor is, it has to be a factor in each one. It has to be a factor in 16, and it also has to be a factor in 28. So let's look at our factors. We have 2 to the 4th factors for 16 and 2 to the 2nd. Each of those numbers have 2 2's in them. So 2 to the 2nd. We cannot list 7 in the greatest common factor because they each do not have a 7 in a factor. So 2 to the 2nd power is 4. So the greatest common factor for 16 and 28 is 4. So you'll notice on the next slide, we're going to put the prime factorization of 16 is 2 to the 4th. The prime factorization for 28 is 2 to the 2nd times 7. We get the greatest common factor, which is going to be 2 to the 2nd, which is equal to 4. So the question was asked, why can't we put 2 to the 4th? Well, they each have at least 2 2's in it. That's why we chose 2 to the 4th power. Let's do some more examples. We're going to find the GCF of the numbers. using prime factorization. Do your factor trees for 90 and 50. Then at the bottom, list your prime factorization with GCF at the bottom. We'll come back and check our trees. The trees could be different, but the totals are the same. So you should have, for the prime factorization of 90, 2 times 3 to the second times 5. Your total prime factorization for 150 should be 2 times 3 times 5 to the second. Our greatest common factor is going to be 2 times 3 times 5. 2 times 3 is 6. 6 times 5 is 30. So the greatest common factor of 90 and 150 is 30. Let's practice it again. Do your prime factorization tree for 84, 216. List the totals. Find your greatest common factor. So you'll notice your trees for 84. You'll notice your tree, for 216. I tallied up my prime factorization. 84 is equal to 2 to the second power times 3 times 7. 216 is equal to 2 to the third power times 3 to the third power. I compared the factors of 2. They each have at least 2 2's in them. They each have at least 1 3 in them. 2 to the second is 4. 4 times 3 is 12. So 12 is the greatest common factor of 84 and 216. So if you have an example of 3 numbers that you've got to find the greatest common factor for, you do the exact same steps. You do the 3 trees, you do the totals at the bottom, and you find the common factor of all 3 numbers. Let's have one more to practice on. Again, we did the trees, totals, 120, there are 3 2's in the prime factorization, 1 3 and 1 5. 192 has 6 2's and 1 3. We compared our 2's, they at least have 3 2's in each, and then 1 3. 2 to the third power is 8. 8 times 3 is 24. So the greatest common factor of 120 and 192 is 24. Now we're going to move to a section where if 2 or more numbers are called relatively prime, if their GCF is 1. Now let's talk about the word relatively. We all have relatives, which means we have a relation. For example, if you have a cousin, maybe you have the same grandmother, or if you have a relation that's an aunt, you have somebody that has something in common with you. So if 2 numbers are relatively prime, what they have in common is that their greatest common factor is going to be 1. Hence, relatively prime. So let's do, on 28 and 45, let's do the upside down division method that we did yesterday. Let's do 28 and let's divide it. Now, the prime factorization of 28 is going to be 2 to the second power times 7. Do the same for 45. Again, we're going to divide with prime numbers. We stop when the last number is prime. So for 45, the prime factorization of that is 3 to the second times 5. So when we're asked to look at the greatest common factor, these 2 numbers do not have any factors that are the same except for 1. So your answer to this would be that these 2 numbers are relatively prime. It's asked to find the GCF of the numbers using prime factorization. Tell whether the numbers are relatively prime. Now, if you can tell by looking at them, that's fine. But the instructions say for you to use prime factorization. So again, use the prime factorization. totals and find the greatest common factor to see if the greatest common factor is 1, to see if they're relatively prime. Now, as you come back to check your trees, we can tell that they have the greatest common factor of 14. So again, in your directions, it said to tell whether they're relatively prime. So your answer is going to be not relatively prime. You need to be sure and answer the question that's given to you. So these two numbers are relatively prime because, it's not relatively prime because they both have a common factor of 2 and they have a common factor of 7. 2 times 7 is 14. So they're not relatively prime, as in the previous example. Okay, we're going to skip this and we're going to go to, let's do 27 and 117. Let's check those two numbers and see if they are relatively prime. Again, after you factor these two numbers out, realizing that they have a common factor of 3 to the second power. 3 to the second power is 9, so they have a common factor of 9. They're not relatively prime. In our last example, this is what you're going to be having word problems using this method. A college class with 30 sophomores, 18 juniors, and 12 seniors is divided into project groups where each group has to have the same number of sophomores, juniors, and seniors. What is the greatest number of groups that can be formed? Class, how many sophomores do we have participating in this? Class?
30.
How many juniors?
18.
And how many seniors? 12. So we need to divide these folks up to where they have the same amount of sophomores in each group, the same amount of juniors in each group, and the same amount of seniors. So we need the same amount of sophomores, juniors, and seniors in each group. So we're going to do the prime factorization tree. Then we're going to determine what the greatest common factor is for all of them. So you'll notice that we did the prime factorization for each one of them. Now we need to find the GCF. GCF for these numbers is going to be 2 times 3 equals 6. So you'll have 6 groups. Now the second part is saying how many sophomores will be in a group, juniors will be in each group, and seniors in each group. Since you have 30 sophomores, you're going to take 30 and divide it by 6 because that's how many groups there are. So you're going to have 5 sophomores. Since you had 18 juniors, you're going to divide it by 6, and that's going to be 3 juniors in each group. Your seniors were 12, so you take 12 divided by 6, 2 seniors in each group. You will need to be well aware of how to use this procedure with that type of word problem. Any questions? Because this is on your test. This is on a graded worksheet. Yes?
I don't understand how you got
Y'all are making too much noise and it's not time to go. Yes?
you got the 5 on
Okay, the GCF. Okay, so I compared 30, 18, and 12. They each had at least 1 2. Then I looked at the 3s. They each had at least 1 3. Can't use the 5. So 2 times 3 is 6. So there were 6 groups. But because I wanted an even amount of sophomores, I took the 30 that I had and divided them into the 6 groups. I had 5 in each group.